stick to a neighborhood of the V1 vertex. So this is given by Z1W, Z2W. You look at the angles. Q1 plus 1 over m Q2. And so you don't have any choice. You take Z1 V1, Z2 V1 to the power 1 over m, and then there is a correction term. So it's again best to just copy from my note, which is, so if I just take product, this is P1 times P hat, that is different from R1, is over here. So if you see what is the difference, this is delta P hat divided by P hat to the 1 over m. Now the important thing is that delta t is t to the 1 over m if t less than epsilon 1. Right? So near w equal to 0, or that is near p hat equal to 0, this is a smooth non-vanishing function because it's 1. Okay? And let me leave some gap. And similarly, let me write down the formula. This is Z2 V1 1 to the m by delta P hat P2 P hat to the 1 over m. So notice that note delta P hat over P hat to the 1 over m is, as well as P2, are non-vanishing. Near P hat equal to 0, that is near, informally I can say near W, because this map rho will take P hat equal to 0 to W point. Okay. So, okay, now here, now I can, of course, because these are non-vanishing C infinity functions, I can make change of coordinate to get rid of this, right? So let me just give you the formula because otherwise. So change coordinates on xv1 as follows. And sorry, so z1 prime v1 to be 1 over square root of 1 over p2 z1 v1, and then these are chosen so that you get what you want. So in these new coordinates, you get what you want. Okay, let me forget these formulas. Okay, so in these new coordinates, rho is given by what you want, z1w equal to z1 v1 times prime times z2 prime v1. This would be an, the point is that this kind of maps are holomorphic. If you take local complex structure given by those coordinates, you declare the coordinates to be holomorphic, right? Then these maps are holomorphic. So that's what I wanted to do. Z2W okay. Okay. So these are the maps I'm giving on these charts. Now also you can check that for a blowdown, it has to be for this resolution, it has to be isomorphism outside the singular set. So here the same thing you can check. So here is the inverse. So this is almost complex with respect to complex structure, local complex structure. Given by the coordinates zi v1 prime and zi w, right? So you can take your local complex structure like this, and this is actually complex. Well, let's retain almost complex. So rho is actually holomorphic locally here. Okay. So let me also tell you what is rho inverse. Well, the formula is easy, right?
Excuse me. What you are doing now is you are describing this blowdown maps.
Yeah. Yeah. Well. So first of all, yeah, I'm describing the blowdown explicitly. I'm giving a almost complex model for it.
So almost complex model for what?
For of course. So blow up, we know how to do in topology, right? But for blowdown, you have to give a specific map, right? And so, and for example, if I have two quasitoric manifolds, my prescription would give you a smooth map. And I want to also define two almost complex structures so that this blowdown map is almost complex with respect to those. So that will form kind of, in my view, a good category. And you see, well, this Chandruan cohomology is defined once you have almost complex structure. And the canonical bundle is, you see, the determinant of the, of the T, of the cotangent, holomorphic cotangent bundle. So even for that, I need almost complex structure. Okay. So rho inverse from rho x v1. Now this final step, I want to show you that this is a diffeomorphism outside the singular set. This rho I constructed, that's what you'd like to have. So, but the formula is, you just make one observation, and this is to xv1 minus p1 p hat equal to 0, or the pi inverse of that. Just write that all that down. So what is this? This is very easy. Z2 prime v1 is Z2w to the 1 over m. Doesn't look 1 to 1 in general, but if you omit that w equal to 0, then locally you can make 1 to 1. And well, if you omit w equal to 0, here's something. We are on charts, right? In the orbifold chart of w, there is a m-fold covering. So that's why you have this 1 over m. But when you go to the underlying space, it just goes away. So anyways, it doesn't bother me. But z1 prime v1 is basically z1w divided by z2w. So this seems, how can you avoid this? Well, you avoid this because of the following. Maybe I can get rid of this picture, or I can show you in the picture even. Okay. Okay. So what is Z2W? The modulus is R2. And what is R2? This is P2 delta P hat. Okay? And this is non-zero if away from P hat equal to 0. That is so in picture, this is what you are doing. Okay, so this is actually non-zero on this image. Let me show you in picture. So you take some neighborhood of this. Of course, you avoid, right? You avoid this point, right? Because x beyond, avoid that point. And when you go down, it never touches this R2 equal to 0 because there is a gap. So anyway, so this thing, map is invertible. That's roughly what I want to say. But now I can finally stitch everything up by saying that I got something that is locally almost complex, right? So finally, I want to say the following, and I do a small calculation. Okay, so similar remarks for vertex. So rho at x v2. So altogether, what I have done is, let me draw that again. I have made an almost complex structure. First, say here, and then, well, I don't know, I mean, here, and then I have an almost complex structure somewhere here. Okay. Now what happens is that this, you see, okay, I had this neighborhood to be precise, and I had this neighborhood to be precise. Now these maps are both holomorphic, right? Rho restrict to V1 and rho restrict to V2. So these almost complex structures are compatible. Okay. So I have an almost complex structure here. Then this is manifold. Then I extend it, because this is positively omni-oriented, I extend this to all those things, because okay, my almost complex structure at V1, V2 is given by the coordinates, and I didn't, all changes I did was in the radial direction. I didn't fiddle with the S1 action at all. So omni-orientation, positive omni-orientation, I can extend it over there. And then by the same logic, now this is inside is manifold, no orbifold singularity. There I can, by the same logic, that SO4 by SU2 is simply connected, I extend it to an almost complex structure on the top, manifold. Now, because this rho map is diffeomorphism, I can push down this almost complex structure, this extended part, and it matches there because that was an extension of the original. So by using the blow down, I can, the fact that this is a diffeomorphism outside the singular set, I can push down. And so now I have two almost complex structures and a map rho that is diffeomorphic, that is almost complex map. Now after doing all this, I can show you this okay, small calculation for the McKay correspondence. Okay. So crepant or not. Okay. So let's write U1 equal to Z1 prime V1 and U2, just to simplify my notations. Let's look at one vertex, okay? And here I have the formulas, okay? So K downstairs, I don't remember what I called. Oh, Y, okay? K, Y, locally generated by dz1w wedge dz2w, and the pullback rho star ky, this is d. Now you plug in those formulas, right? So this is Z1, sorry, so U1 times U2 to the 1 over m wedge d of U2 to the 1 over m, and you calculate. So this is U1, U2 to the 1 over m du1 wedge, you have a 1 over m U2 to the negative 1 over m plus 1, right, du2. So this is, what is this? This is 1 over m U2 to the 1 minus 2 over m, sorry, I made error, right? So this is 1 over m minus 1 du1 du2. So kx generated near v1 by du1 wedge du2. So they're equal, the pullback equals this. So crescent rho star, okay, k y is kx near locally at least, and then you can do it if 1 minus 2 over m equal to 0, and so m equal to 2. Okay? Now if m equal to 2, let us say that the Chandruan cohomology will match. So suppose m equal to 2. Now what we have here is that W GW. Okay, so what were the characteristic vectors? That was 1, 0 and minus 1, 2 now, because m is 2. ZW is just the cyclic group of order 2. Right. And so H star, H orb of, okay, Y, it has two pieces. Okay, so now let me also calculate this degree shifting number for you, because, well, the action is, let me just believe me, maybe. I showed you the action at some point for any orbifold singularity. The action here is, okay, so this is say 1 and G, and the action of G on Z1W, Z2W, you can check, this is just minus Z1W minus Z2W. That's what you would expect, maybe. This is probably the only only action as a finite subgroup of SL2, right? It has to preserve determinant, so it's got to be like this. So this is e to the 2 pi I half Z1W e to the 2 pi I half Z2W. So iota of G is half plus half equal to 1. Twice iota G is 2. So there are two contributions to this orbifold thing. One is H H of Y, whatever, plus this is corresponding to G equal to identity. Okay, that's the Chandra one. Plus there is only one non-trivial. I'm assuming all other points are smooth. Only one contribution, which is this H. What is a fixed point? That's just a single point. So H H of pi inverse W. So it's got to be H0, and this is of degree twice iota g equal to 2 because of the degree shifting of Chandran cohomology. And now what do you have? When you do the blow up, you introduce a new sphere that gives you a new class in H upper 2. And that corresponds to the contribution from this. So that's the thing.
What is your final statement of this?
Okay, the final statement is that given any so the ideal theorem would be that given any four-dimensional quasitoric orbifold, you can resolve it by a sequence of blow-ups. That you can do. That is easy to.
Statement is what?
Now, what you would like an almost complex structure on the orbifold and the final resolution, so that this blowdown is almost complex and there is Mackay, this type of correspondence in Chandran cohomology. I cannot do that because my process is not inductive. What I can do is the following. For any blowdown between, like a single step blowdown, I can put two almost complex structures and correspondence in Chandran cohomology. I can even go to composition of two blowdowns, but I don't know a. So there is some combinatorial kind of difficulty that I haven't been able to figure out. Yeah, four-dimensional case. A higher dimensional case, we haven't even been able to yet put a almost complex structure on, say, a six-dimensional quasitoric orbifold, because this SO6 by U3, that is no longer simply connected, something like that.
So the statement is that when you have a positive four-dimensional positive omni-oriented
quasitoric
orbifold, then you can give us almost complex structure there, and then you can blow up or blow down.
Blow up or blow down.
Blow up or blow down. Still, you give almost complex structure so that this flow net is
almost complex, and if it is crepant, then Chandran cohomology is same.
But if you do one step or one blow or
I can do two blowdowns. But okay, so there is one stupid thing like that you cannot. I can, even for a series of blowdowns, I can give two almost complex structures, candidates, so that the blowdown would be holomorphic, but I cannot just prove it. This has to be true, but you see, an arbitrary sequence of blowdowns, it's hard to write down a formula for it. It could be n number of blowdowns, and I just haven't been smart enough to get around this, because so something maybe, you need to find some clever argument to get around this, so that you don't have to. Here I wrote down one formula, right? For a sequence of n blowdowns, if you want to write a formula, you'll be quite lost, because there would be these delta functions at each step and various combinations of them. So you need like a clever argument, and that I haven't been able to give yet.